All right, now let's look at other periodic trends. Since now we understand the trend of atomic size. Now we are going to look at another trend called ionization energy, and we will look at electron affinity afterwards. And then ionization energy is the minimum energy required to remove an electron from 1 mole of a ground state gaseous atom. Right. Ionization energy measures how tightly electrons are held in an atom. Right. Think about the size of an atom as well. What makes the size of an atom the way it is? So low ionization energy means low ability to resist the loss of electrons. High ionization energy means a very high ability to resist loss of electrons. All right, so for example, the metals, okay? So in general, metals have low ionization energy. What does this mean? It means in general, metals, all right, metals are prone to losing electrons, or rather have a low ability to resist loss of electrons. Or rather, metals need less energy right to remove electrons. Right, and in general again we have nonmetals. Nonmetals in general have high, or rather high ionization energy. All right, this means that they have a high ability to resist the loss of electrons, which means, okay, they need more, all right, more energy to remove electrons from them. Right, so that's what ionization energy is in a nutshell. Now let's look at electron affinity, because these two are related. Right, so electron affinity, right, refers to the energy that is released, all right, or energy change when electrons are added to 1 mole of gas phase ground state atom. All right, so how do we interpret it? Okay, a positive electron affinity means energy is released. Right, electron addition is favorable and an anion is stable. Right, high electron affinity means more ability to gain electrons. So high means more ability to gain electrons, and low electron affinity means low ability to gain electrons. Right, so in this case, so in general now we can say that metals, right, have low electron affinity. What does this mean? Right, it means that they release less energy right when electron is added. Right, when an electron is added. All right. So what does this mean? It means, all right, if they release less energy when an electron is added, it means they don't like, right? They don't like gaining, okay? Don't like gaining electrons. All right. And then in general, we have nonmetals, which have high electron affinity. All right, what does this mean? It means they will do anything. They will release a very high amount of energy to gain that electron, and that makes them stable. Okay, release high or more energy, right, to gain, right, to gain electrons. All right, so in other words, they like gaining electrons. All right, so now let's resolve the issue between the two concepts, electron affinity and ionization energy. All right, ionization energy refers to the ability to resist losing. Right, if you think about it, if something doesn't have a very high resistance, all right, so likely if it cannot resist losing, right, it's likely not going to want to win. Think about it as a soccer game, right? If you think about it as a soccer game or any game at all, if a team is a very tough team, all right, and this team hates to lose, okay? For example, in this case, it would be non-metals. It hates to lose. It has more ability to resist loss. So if it has more ability to resist a loss, right, it will also have a higher ability to gain a win, right, or to win, right? So that's where ionization energy and electron affinity are related. If you got more energy to win, then you've got low energy to lose. All right, so this is where electron affinity and ionization energy come together. When an atom has a low ionization energy, it means that it doesn't have much strength to resist, all right, an electron being taken away or losing an electron, all right? So it doesn't have much strength to resist a loss. Think about it as a game, right? If we are playing a game between two teams, the team, right, that cannot resist an attack, right? It has a very low strength in resisting an attack, right, will most likely lose the game, right? And if in terms of winning the game, will less likely win the game. So this is where these come together. Right. It is more likely to lose and less likely to win. Okay. So it's almost like a same thing, right? Just being explained in different ways. Right? If you are likely to lose, you are less likely to win, right? You don't like winning. And if you are less likely to lose, which means high ionization energy for non-metals, if you are less likely to lose a game, then you are more likely to win. So therefore, the non-metals are less likely to lose electrons. okay, less likely to lose electrons, all right? At the same time, in terms of electron affinity, all right, they are more likely to gain electrons, right? So that's where this all comes together. When you measure the ability of an atom to gain or win an electron, all right, you measure it using the electron affinity, right? So, and when we look at the average of these two, that's what makes what we call electronegativity, all right? So elements that have low ionization energy, okay, so elements that have low ionization energy, they also have, all right, they also have what? A low electron affinity, right? So low value plus another low value, when you take the average of that, is going to be a low value. So in that case, these elements, most likely metals, right, will also have a low electronegativity. All right, and so these are metals. And if one has a high value, high ionization energy, they also have high electron affinity, and this leads them to a high electronegativity, because that's just the average. You take the average of two high values, you get a high value. You take an average of two low values, you get a low value. All right, so to define electronegativity, electronegativity is a measure of the tendency of an atom to attract electrons from another atom to which it is bonded. All right. So in this case, right, electronegativity is not measured by any instrument, right? It's just an average of the two, which is electron affinity and ionization energy. Right. Ionization energy and electron affinity, they are measured energies, right? The energies required for either to lose or to remove an electron, or for an atom to gain an electron. So the average of that is electronegativity. All right, so that means that the trend of ionization energy, electron affinity, and electronegativity are the same. So ionization energy, electron affinity, and electronegativity generally decreases as you move down the group and increases as you move across the group. Wait a minute. This just looks like an opposite of atomic size. So, right, let's look at that. Okay, check atomic size here. If you check atomic size, when you move down the group, increases, right? And when you move across a period, atomic size decreases. So in this case, we can say, okay, I'm gonna just show you now. All right, so the relationship between atomic radius or atomic size. So I'm just gonna use atomic radius. So I'm gonna represent the radius, all right, with the symbol, right, I'm gonna represent it with the symbol R, right? So it means that the atomic radius is inversely proportional to the ionization energy, right? Again, the atomic radius is also again inversely proportional to the electron affinity. Again, the atomic radius is inversely proportional to the electronegativity, right? So now, if you understand the trend of the atomic radius, then you know that the other trends are opposite to the atomic radius. So in a nutshell, I can say that the atomic radius is inversely proportional to the ionization energy, electron affinity, electronegativity, right? Is inversely proportional to all these three. So which means if the atomic radius is increasing, right? For example, as you go down the group, the atomic radius is increasing. The size of an atom is increasing. Then what happens to ionization energy, electron affinity, and electronegativity? They are all decreasing. Okay. That is down the group. Down the group. What if you are moving across a period? All right. So atomic radius, we know that is inversely proportional to ionization energy, electron affinity, electronegativity. All right. So as you move across, okay, across a period, as you move across a period, what's happening to the atomic radius? Right, because of increasing nuclear charge, the atomic radius is getting smaller because of increased attraction between the nucleus and the electron cloud. So the electron cloud shrinks because of stronger electrostatic forces of attraction. So atomic radius decreases as you move down the group. And what happens to ionization energy, electron affinity, and electronegativity? They increase. And for this reason, nonmetals have a very low ionization energy, electron affinity, and electronegativity, whereas the nonmetals have a very high ionization energy, electron affinity, and electronegativity. So now let's answer this question. Let's arrange these three, right? Let's arrange this list in order of increasing ionization energy, electron affinity, and electronegativity, because the trend of these three is the same. All right. So for the first one, nitrogen, oxygen, and fluorine. Right. So we know that on the periodic table, right, the first one is oxygen, followed by the first one is nitrogen, followed by oxygen, followed by fluorine. All right. As we move this way, what is happening to the atomic radius? We know that the atomic radius is getting smaller. Right. If the atomic radius is getting smaller, it means these are getting bigger. Right. So it means that they are increasing. All right, so if that is the case, then we can say that the first one is already in increasing order of ionization energy, electron affinity, and electronegativity. So this one is already correct. All right, so for lithium, potassium, and caesium, we can know that lithium is at the top of the group, and then we have caesium at the bottom of the group. Right. So in this case, how is atomic size like? So as you move down the group, okay, as you move down the group, what's happening to atomic size? Because of increasing energy levels, right, the atomic size R is increasing. So if the radius is increasing, it means ionization energy, electron affinity, electronegativity, they are all decreasing. Okay, and if that is the case, if they are decreasing as we go down the group, it means the one at the bottom has low, right? And the ones at the top have high. All right. So now we can now arrange them. So which means the lowest one is cesium, followed by potassium, followed by lithium. All right. Same thing with bromine, chlorine, and iodine, which are on the third one. So we are basically, if we put them according to the group, we know that chlorine is at the top, followed by bromine, and then followed by iodine. So as we move down the group, right, we know that the atomic radius is increasing. And if it's increasing, therefore, ionization energy, electron affinity, electronegativity, they are all decreasing. If they are decreasing, it means that the lower one is at the bottom, the higher one is at the top. So if we order them from lowest to highest, it will be from iodine, all right? Iodine less than bromine, less than chlorine, right? So that's how we would have done that as well. So you can represent it with a less than. I think it's more appropriate symbol to organize it with. Okay. Okay. Like that. Right. So basically, guys, that's how to answer questions in periodic trends.